Hello everyone, I'm Takashi from NTT. Today I will give a merged talk of these two works. They are joint works with Nai-Hui Chia, Chan, and Qipeng. ZeroKnowledge proofs and arguments are fundamental primitives in cryptography. In this primitive, a prover tries to convince a verifier of truth of some statement without revealing anything beyond the truth of the statement. Formally, we require the following three properties. First is the completeness, which means that if the statement is true and everything is done correctly, verifier accepts with overwhelming probability. The second is the soundness, which means that if the statement is false, then no matter how the prover tries to cheat, the verifier accepts with negligible probability. The third is the ZeroKnowledge property, which roughly means that verifier learns nothing beyond the fact that X is a true statement. And next, I will explain a little bit more detail about the definition of the ZeroKnowledge property. The formal definition of the ZeroKnowledge property is given as follows. For any verifier, there exists a simulator. For any distinguisher, distinguisher doesn't distinguish the following two words. The first is the real world, where verifier gets some auxiliary information, interact with the honest prover, and finally outputs some output. On the other hand, in the ideal world, simulator that depends on verifier gets the same auxiliary information and outputs some outputs without interacting with the honest prover. So this means that everything the verifier outputs after interacting with the honest prover can be simulated without interacting with the prover. And so this means that verifier doesn't learn anything from this interaction. And especially there are several variants of ZeroKnowledge, and the first is classical ZeroKnowledge, where everything V, S, D, and O's are classical, and in the quantum ZeroKnowledge, V, S, D, O's are quantum. And we also sometimes allow simulator to be expected polynomial time rather than fixed polynomial time. And when it depends on the context whether we consider expected or a strict polynomial time simulator. And especially we consider a subclass of ZeroKnowledge property called BlackBox ZeroKnowledge. So the difference from the general ZeroKnowledge property is that simulator is limited to those that only uses a verifier as a black box, and this is the only difference. And so this is a stronger requirement than the standard ZeroKnowledge. So here are several reasons why we study BlackBox ZeroKnowledge. The first reason is that most known protocols satisfy BlackBox ZeroKnowledge, and second, there are very few non-BlackBox simulation techniques, and third, protocols with non-BlackBox ZeroKnowledge are usually far from practical. So for those reasons, we believe that it is quite important to study the power and the limitations of BlackBox ZeroKnowledge. And especially in this work, we focus on post-quantum ZeroKnowledge. Post-quantum ZeroKnowledge protocols are classical protocols with quantum ZeroKnowledge, and especially we focus on those for NP languages. And because we already know a lot of constructions of classical ZeroKnowledge protocols, so one may think that we can obtain post-quantum ZeroKnowledge by just replacing those assumptions with post-quantum assumptions in the classical ZeroKnowledge protocols. However, this doesn't work in general because of the usage of so-called rewinding technique that doesn't work in the quantum setting. Therefore, for constructing post-quantum ZeroKnowledge protocols, we need a new proof technique that is inherently different from the classical counterparts. And here I review some known constructions of classical and post-quantum ZeroKnowledge protocols. And I remark that this is not the exhaustive list of known constructions, and I just picked some most relevant works to our work. So the first classical ZeroKnowledge proof for ORNP language was given by Goldlaihi, Mikali, Wigderson based on one function. However, their protocol has polynomial number of rounds if we require negligible soundness error. And after that, it is one of the most important topic in the study of the knowledge to reduce the number of rounds. And by now we know a lot of constant round constructions of the knowledge proofs and arguments like those. However, because these constructions are only proven to be classical zero-knowledge, and it was not immediately clear if these constructions are post-quantum zero-knowledge, even if we rely on post-quantum assumptions. So the first post-quantum zero-knowledge protocol is obtained by Watrous in 2005. So he proved that many known constructions of classical zero-knowledge proofs are actually also post-quantum zero-knowledge if we rely on post-quantum assumptions. However, his technique is only applicable to protocols with a super constant number of rounds. Therefore, after his results, it has been a long-standing open problem to construct constant round post-quantum zero-knowledge proof or even argument. This open problem was recently solved by Bitansky and Shimeli. However, their construction, their security proof relies on a novel non-black box simulation technique. So this means that their protocol doesn't satisfy black box zero-knowledge property. Therefore, the following question is natural to ask. Are there constant round post-quantum black box zero-knowledge protocols? And in this work, we give both positive and negative answers to these questions. So first, I would like to introduce our main impossibility result. So we prove the following theorem. There does not exist a constant round post-quantum black box zero-knowledge argument for NP even with quantum expected polynomial time simulation unless NP is contained in BQP. And first, I would like to remark that this theorem demonstrates an essential difference between classical and post-quantum black box zero-knowledge because in the classical setting, we know the construction of constant round classical black box zero-knowledge proof with expected polynomial time simulation. So this is a fundamental difference between classical and post-quantum setting. And second, this theorem justifies the non-black box simulation in Bitansky and Shimeli because black box simulation is impossible in constant round. On the other hand, we may want to know how much we can achieve by black box simulation in constant round, even though the full zero-knowledge is impossible. So for this direction, we also consider a weaker version of zero-knowledge. The weaker version of zero-knowledge we consider is called epsilon zero-knowledge. For explaining the definition of epsilon zero-knowledge, I first recall the definition of the standard zero-knowledge. So the standard zero-knowledge says that the difference between these two probabilities is upper bounded by negligible function. So by the definition of the negligible function, this is equivalent to this. For any inverse polynomial epsilon, this is upper bounded by epsilon. So this is just based on the definition of the negligible function. And the epsilon zero-knowledge is a variant where the order of quantifier is a little bit swapped. That is, the epsilon comes before a simulator. This means that a simulator can depend on epsilon. And so this slightly weakens the requirement of zero-knowledge. However, we believe that epsilon zero-knowledge is just below zero-knowledge due to the following reasons. First, epsilon zero-knowledge implies weaker notions of zero-knowledge, such as weakness in distinguishability, weakness hiding, etc. Second, epsilon zero-knowledge is sufficient for many game-based security applications of zero-knowledge proofs and arguments. And third, achieving epsilon zero-knowledge is usually as hard as achieving zero-knowledge in the classical literature. So we believe that epsilon zero-knowledge is very mild relaxation of zero-knowledge. So by weakening the zero-knowledge property to epsilon zero-knowledge, we obtain the following two positive results. The first is a proof based on any collapsing hash function which is considered as a quantum counterpart of collision-resistant hash function. And our second construction is an argument based on any one-way function. So far, I explained that post-quantum black box zero-knowledge in constant round is impossible, but post-quantum black box epsilon zero-knowledge is possible in constant round. Then the next natural question is if there is some lower bounds for post-quantum black box epsilon zero-knowledge. And for classical zero-knowledge, we know several impossibility results like 3-round black box zero-knowledge and constant round public coin black box zero-knowledge. And we give similar lower bounds for post-quantum black box epsilon zero-knowledge. That is, there doesn't exist 3-round or constant round public coin post-quantum black box epsilon zero-knowledge argument for NP unless NP is contained in BQP. And I remarked that this similar theorem was also proven in a concurrent work by Bitansky, Kerner, and Schimeli. So this is the summary of our results. So we proved that constant round post-quantum black box zero-knowledge is impossible. On the other hand, we show that 5-round post-quantum black box epsilon zero-knowledge is possible. On the other hand, 3-round or constant round public coin post-quantum black box epsilon zero-knowledge is impossible. And then the natural open question is, how about 4-round? So in the classical setting, we know some constructions of 4-round black box zero-knowledge. However, our proof technique is not applicable to those protocols, and so we leave it as an open problem to construct 4-round black box post-quantum epsilon zero-knowledge proof and arguments. From now, I will move on to the technical part. Due to time constraint, I will only focus on the main impossibility result, which is the impossibility of constant round post-quantum black box zero-knowledge. Our starting point is the following classical theorem proven by Bark and Lindell. So they prove that there does not exist constant round classical black box zero-knowledge with strict polynomial time simulation for NP unless NP is contained in BPP. For proving this theorem, their core lemma is the following. For verifier that aborts with probability 1 minus epsilon, where epsilon is some inverse polynomial in each round, then a simulator must rewind the verifier at least polynomial of epsilon inverse times to correctly simulate the view of the verifier. The intuition behind the lemma is that because a verifier aborts with probability except for very small probability epsilon, so the simulator has to rewind the verifier sufficiently many times to get useful information from the verifier. And this lemma easily implies theorem because epsilon can be set to be arbitrary small inverse polynomial, in which case simulator's running time cannot be upper bounded by fixed polynomial. Here, our observation is the following. This lemma essentially means that the simulator must learn epsilon because the simulator decides how long it runs depending on the value of epsilon. Then our idea toward our impossibility result is the following. if the verified aborting probability is controlled by an auxiliary quantum state, then the simulator must collapse the state because it must learn the aborting probability. On the other hand, we can show that such a collapsing doesn't happen in the real execution, and as a result, we can show that the difference can be noticed by the distinguisher, and this means that simulation fails. For making this intuition to be a rigorous proof, we have to do the following two things. The first is to prove the quantum version of Barak and Linder lemma, and the second is to complete our impossibility result based on the quantum version of Barak-Linder lemma. And next, I will talk about a little bit more details of each step. So first, I would like to explain how to prove the quantum version of Barak-Linder lemma. But before that, let me recall how the classical version was proven. So the Barak-Linder lemma says that for verify that abort with probability 1 minus epsilon in each round, a simulator must rewind the verifier at least polynomial or epsilon in both times. And the intuition of the proof of this lemma is the following. Suppose that the number of simulated queries to the verifier is not large enough, then we can show that simulator cannot see two forking transcripts, which are two different transcripts that are identical to until certain rounds but different from that round. And then, suppose that the simulator doesn't see such two forking transcripts, then this means that simulator essentially just interacts with verifier in a straight line session. Then we can embed the real verifier's messages into the responses to queries to the simulator for such a straight line session, and as a result, we can reduce the probability of simulator outputting accepting transcript to the probability that the cheating prover can let the verifier accept. Therefore, by the soundness of the protocol, if x is false, this probability is negligible. On the other hand, if x is a true statement, then we can show that this probability is lower bounded by epsilon to the k minus negligible, or where k is the number of rounds. This is because in the case of yes instance, simulator has to correctly simulate the real execution. And in the real execution, because we are considering a verifier that aborts with probability 1 minus epsilon in each round, and because we have k rounds, so the probability that verifier accepts is epsilon to the k. Therefore, for the simulator to correctly simulate this execution, this probability should be negligibly close to epsilon to the k by the ZeroKnowledge property. And because we set epsilon to be inverse polynomial, here is a noticeable gap between no instance case and yes instance case. Therefore, this means that L can be decided by polynomial time, which means that L is in BPP. So this is the proof sketch of the Barak-Linder lemma. Next, I will explain how to prove the quantum version of this lemma. And the quantum version is almost the same, except that we consider quantum simulator that quantumly queries the verifier and changing the assumption to be NP contained in BQP. So basically, the proof structure is similar, and especially for the yes instance case, this can be done almost in the same manner. On the other hand, for the no instance case, this is a little bit non-trivial because in the classical case, we embedded the real verifier's messages into responses to simulated queries. However, now we are considering quantum simulators that make quantum queries. In that case, it is non-trivial how to embed classical messages into such a quantum queries. To resolve this problem, we rely on the measure and reprogram lemma developed in the context of Fiat-Shamir transform in the quantum random model. Very roughly speaking, this lemma means that even if we randomly measures a constant number of random queries of the simulator's success probability decreases only by a factor of polynomial. Therefore, first we apply this lemma to measure k randomly chosen queries of the simulator, and then we embed the verified messages into these measured queries. And in this way, we can reduce the probability that simulator outputs accepting probability to the soundness of the protocol. Next, I will explain how to use the quantum version of Barak-Lindley lemma to prove our main impossibility result about constant round black box post-quantum zero-knowledge. Suppose that we have a simulator whose expected number of queries is q. Then, by Markov inequality, the probability that the number of queries is more than 2q is larger than 1/2. And then we take inverse polynomial epsilon so that 2q is more than polynomial of epsilon inverse, where this polynomial is chosen so that we can apply the quantum version of the Barak-Lindley lemma. Then let's consider a malicious verifier v tilde that takes a control qubit initialized as a uniform superposition of 0 and 1 as auxiliary input and runs either of the honest verifier or 1 minus epsilon avoiding verifier controlled by the control qubit. That is, if the control qubit is 0, then it runs the honest verifier. And if that is 1, then it runs the verifier that aborts with probability 1 minus epsilon in each round. And it runs these two verifiers in superposition. And let's see what happens in the real world and in the simulation for this verifier. In the real world, conditioned on verifier's acceptance, the control qubit collapses to this state. This is because in the case of control qubit is 0, it behaves as the honest verifier that always accepts. On the other hand, in the case of control qubit equal to 1, it behaves as 1 minus epsilon avoiding verifier that accepts with probability epsilon to the k. Therefore, condition on verifier's acceptance, the control qubit collapses to this state. On the other hand, in the simulation, condition on number of queries is more than 2q and verifier's acceptance, the amplitude on 1 should be negligible by the quantum version of Barak-Lindley lemma. This is because we choose epsilon small enough so that 2q queries are not enough to let the verifier accept or with non-negligible probability. Therefore, the amplitude on 1 should be negligible when the number of queries is more than 2q. Moreover, as seen here, the probability that the number of queries is more than 2q is larger than 1/2, and the condition on that the number of queries is more than 2q, the verifier's acceptance probability is at least 1/2 because no matter how many queries the simulator makes, the honest verifier always accepts, and v tilde is a uniform superposition of honest verifier and 1 minus epsilon avoiding verifier, and so in the case of honest verifier, which happens with probability 1/2, it always accepts. Therefore, in total, this event occurs with probability at least 1/4. Therefore, we can see that the final state of the control qubit is non-negligibly different condition on some event that happens with constant probability. Therefore, the difference can be noticed by the distinguisher by the swap test. So this is a summary slide. We proved several impossibility and possibility results about constant round post-quantum black box zero knowledge. And due to time constraint, I only talked about the detail of the first impossibility result. For the details of other results, please see our paper. This is the end of my talk. Thank you for your attention.